Hello everyone, I am Muhammad Ishfaq from Jiangsu University and our presentation topic is Enhancing FSCS ART through test input quantization and inverted list. First of all, we will give the introduction of search field and then we will talk about the factors for nearest neighbor search algorithm to be used in FSCS ART, and then what is the approach for enhancing the efficiency, and then the QIVFSCS-ART framework. Our proposed method will be introduced. After that, illustration of the proposed method and then results. In the end, we will conclude the presentation by giving a brief summary. Adaptive random testing is an extension of random testing which works on the exploiting the clustering of failure regions of software. As we can see in the figure 1 that the many software failures tend to cluster to form contiguous regions in the software input domain. Those regions can be characterized into block, strip pattern or point failure pattern. So the motivation of ART is that if a test case is unable to find a failure in software, the next test case should be selected that is far away from previously executed non-failure causing test cases. So fixed size candidate set ART, FSCS ART is a widely used, first proposed and simple to use ART technique that is a distance based technique, and it initializes its algorithm by making two test case sets, candidate test case set and executed test case set. Both are empty in the beginning, and after that we randomly generate a specific number of test cases in candidate test case set, and then we calculate their distances with the previously executed test case sets, and then we select a candidate test case whose nearest neighbor is at the farthest distance from the other candidate test cases. So in this way it uses min max strategy. So in the end, the goal of FSCS is to even spread test cases across the software input domain, which incorporates diversity into testing process. So here is an illustration of FSCS ART. Black dots represent the previously executed test cases and those circles represent the candidate test cases. In the first process, the distance of candidates with the previously executed test cases will be calculated and then its nearest neighbor will be found. C2 will be identified as the nearest neighbor of C1, and similarly T1 will be identified as the nearest neighbor of C2. In the third step, test case will be selected from which has the farthest nearest neighbor. So in this way, C2 will be selected as the next test case. FSCS ART achieves even spread across the software input domain as compared with the random testing. So as we saw that the main working of FSCS rotates around the finding nearest neighbor. So nearest neighbor search, widely used research topic in software testing and computer science. The exhaustive nearest neighbor calculation means FSCS ART calculates distance of candidate test case with all the existing test cases. So its complexity is quadratic complexity. We hypothesize that a good nearest neighbor search algorithm can alleviate the computational overhead of FSCS ART. So we have listed the properties of the nearest neighbor search algorithms. We have analyzed it from the perspective of FSCS ART, and we have listed that which properties are desired in our problem and which properties are not desired. We selected an approach that uses quantization, k-means clustering, nearest neighbor search by quantization, and inverted file index to enhance the efficiency of FSCS ART. So quantization is a destructive process to reduce the input domain's cardinality, mainly when input data is real valued. So quantizer is basically a function that maps d-dimensional vector to a vector that has low cardinality and to another set C, which is a subset of the vector space. So the reproduction values Ci belong to C are called centroids, and set of reproduction values is called a codebook of size k. So the vectors Vi mapped to given index is referred to as a cell, and X. So the k cells of a quantizer form a partition of Rd. It means that the cells basically they partition the input domain into several Voronoi cells, A vector must be quantized into to its nearest codebook centroid using Euclidean distance. So we can see that this is our input space, and k-means, after running k-means clustering after several iterations, it generates Voronoi cells into the input domain. These crosses show the centroid of this Voronoi cell, and all the data vectors are belong to this Voronoi cell. Nearest neighbor search by quantization is where we have a query point, and first of all we calculate the distance of query point with existing centroids. After that we find the nearest centroid, and then we go down into this cell, that cell, and we calculate the distance of query point with the points that lie inside that Voronoi region. In this way, the nearest neighbor complexity scales down to n log k. But we can further increase the efficiency of this process by using inverted file index. Inverted file index is a modified form of heap data structure mainly used in information retrieval. It converts the regular index into the inverted list by quantizing centroids and indices of dataset vectors in the corresponding lists. So in this way we only have one list, and in this way when we will find the centroid, we will directly go into its inverted list to find the other vectors. In this way the nearest neighbor search complexity scales down to go n over k. So we use the framework that is called QIVFSCS-ART that uses quantization and inverted file index. It has basically four major steps, phases, which are the initialization phase, cell formation phase, insertion by quantizer, and nearest neighbor search phase. So in initialization phase, the first step, we specify some parameters. For example, D is the software input domain, and list is the number of cells to be created in D, number of Voronoi regions. N probe is the number of cells out of N list to be visited for nearest neighbor search. We will discuss this parameter in detail in the upcoming slides. And N is the number of random vectors for cell creation for k-means clustering. These are vectors to be used for the clustering and for making cells. And size, S is the size of candidate test case set. In the next step is the cell formation step, where n least number of cells are created in input domain D using k-mean clustering. The problem is that k-means clustering requires training dataset beforehand, but in FSCS ART the dataset is initially empty. So as a solution we use, as we see here, we use n number of random vectors. We generate these n number of random vectors in the software input domain, and we run k-means clustering for 20 times and on 0.1 million vectors. So in this way we make cells in software input domain. After that we randomly generate a test case and we test software for that, and in the next step we insert that test case into the cell. So this is insertion by quantizer. First of all we will quantize it, and then we will assign the relevant cell of that in test case, and we store it into the inverted file structure. Next we check the termination condition, whether it is satisfied or not. There can be multiple termination conditions, for example time elapsed, number of test cases generated, or failure is revealed or not. If termination condition is not achieved yet, we go further and we generate S number of candidates in the candidate test case set. And now the main contribution of our method starts here. Here we will calculate the nearest neighbor of each candidate in Voronoi cells. So coarse search, it is the rough search that finds the nearest neighbor of each candidate, that finds the cell, the relevant of cell of this candidate test case. So for example we can see that this candidate test case lies in this region, but probe parameter specifies the nearest centroids for each CI. So if the n probe is 3, it means not only this cell, it will also find this cell and its centroid, and also this cell and centroid. Why this parameter is necessary? Because sometimes there can be the case that the nearest neighbor of this candidate may lie in another cell. So in the next step, the fine-grained search, we will go further down into these cells and we will calculate the distance of this candidate test case with all the test cases that lie within those regions. So in this way we find the nearest neighbor of the candidate test case will be found for all those test cases that are generated in C, and then we will select the min-max strategy. Using min-max strategy, the candidate test case that is at the farthest distance will be selected as the next test case, and the process will be repeated, and in the end we return the test cases generated. Here is an illustration of our method. In the first step, we used k-mean clustering and a number of randomly generated test cases are 500, and we used 5 centroids. So it resulted 5 centroids in the input domain of software. And in the next step, there are some test cases that are generated in this input domain, and these test cases belong to exactly one of the created centroids. In the regular index we can see the list. For example, T1 belongs to C2 here. So after that, to find the nearest neighbor of query point Q, we will calculate the distance of Q with all the centroids, and this will give us C1, and then we will go down to find all the test cases that lie in this cell. So we will go C1 is the quantized form of this test case, this point. So we will go down and we will find T2 and T3, and we will calculate the distance of Q with T2 and T3, and we will find the nearest neighbor. In this way we can see that a lot of distance calculations have been skipped. So the results of our method can be divided into two categories: efficiency results and effectiveness results, because the aim of our method is to increase the efficiency of FSCS ART, but at the same time we want to maintain the failure detection effectiveness of FSCS ART, because FSCS ART is already a very popular and highly effective ART method. And so in terms of efficiency, we used time to generate a specific number of test cases, and we can see that in various dimensions. This was 2-dimension, 5-dimension, 10 and 15 dimensional input domain, and we can see that FSCS ART is always quadratic, and QIVFSCS-ART always takes less number of time to generate the test cases. There are two main results that are to be noted. To generate few number of test cases, relatively less than 5,000, FSCS-ART is little faster. Why? Because it does not have any mechanism of k-means clustering, randomly generating test cases, partitioning the input domain into cells, so it directly generates those test cases, so it is faster. But when we need to generate a huge amount of test cases, that is the most realistic scenario, our method becomes apparently better. The second observation that we can see is that our method QIVFSCS-ART is least affected by the curse of dimensionality. For example, to generate 20,000 test cases in 2-dimensional input domain, our method takes around 5 seconds. FSCS takes 9 seconds. But same number of test cases when needed to be generated in 15-dimensional input domain, we can see that FSCS-ART takes 15 seconds, but still our method takes 5 seconds. Real life software are high dimensional, still our method is very nice in those scenarios. In terms of effectiveness, we used F ratios, the number of test cases, to find the first failure compared with random testing. For example, 69 means random testing takes 100 test cases, but FSCS-ART takes 69 test cases. But at the same time, QIVFSCS-ART took 71 test cases. So the results in both block, strip and point failure patterns are almost similar to each other. For example, here if it is a little worse, but here our method is better than FSCS ART. But overall analysis of these results says that the both methods have comparable failure detection effectiveness. So in this paper, we propose an efficient version of FSCS ART using quantization and inverted file structure, QIVFSCS-ART. Method partitions the software input domain into several Voronoi cells using k-means clustering, but then it uses quantization and inverted file index to find the nearest neighbor of the candidate test cases. The results show that the method is highly effective, highly efficient while preserving the failure detection effectiveness of FSCS ART. In future, the number of cells that we have created are fixed, like we created only 100 cells in the software input domain. This should be dynamic because as the number of test cases, the executed test cases increase, the number of cells should also increase. And also researchers can also try to use the GPU version to enhance the efficiency further, and also other quantization approaches, for example binary quantization and product quantization, are also needed to be considered. So that's all from my side. Thank you very much. I will be very happy to take your questions and queries. And for the moment I am also looking for a doctoral position. If supervisor is interested, you can contact me my email address. Thank you very much.